This is Dr. B, and let's take a look at nuclear processes. This is an overview. They are processes that alter the nucleus of an atom. So you're messing with the nucleus, whereas in a chemical process, you're typically retaining the number of neutrons and protons. You're changing things that deal with the electrons. So it's a big difference. Chemical processes and nuclear processes are fundamentally different. When does a nuclear process occur? It happens when you don't have enough binding energy in the nucleus. In practice, this means you do not have that magic neutron to proton ratio of 1 to 1.5. So for example, if you had 100 protons, you could handle up to 150 neutrons. More than that, and the nucleus is unstable, as shown in this graph. It's a nice way to predict if you've got a dangerous isotope. When they do decay, they can do by various processes. These can include alpha decay, which has that symbol, beta with the negative sign, gamma, and positron, which is beta with the positive sign. And we can show what they are using this format here, where A will be our element, the charge will be shown there. Sometimes this will be left out so that we can focus simply on the protons and the neutrons. This is known as the atomic number. This defines what element it is. For example, if that's the number 2, it's helium. When you add to it the neutrons, you get the mass number here. So let's have a look at this one. This looks like a helium atom, but since it has a +2 charge, it's more properly called a helium ion, or perhaps even a helium dication. This would be called helium-4, since you really don't have to include the 2. It has to be 2 for helium. That would be helium with 2 protons and 2 neutrons. We're going to see this is known as an alpha particle. It could also emit an electron. Notice the -1 charge. That makes sense for an electron. What doesn't make so much sense is it has -1 protons and no neutrons plus protons. Pretty weird, right? But this will make sense when we look at it further. Let's just define it as that. We'll see that this is known as a beta particle. This looks like it has no protons or neutrons or charge. This is pure energy, known as gamma radiation, sometimes called a gamma particle. And here's another one. It's an electron with a +1 charge. What? This is known as a positron. We'll have more to say about these in subsequent slides. If they look confusing at first, you're not alone. But we can balance these pretty easily. So for example, if we are starting with uranium-238 and we find that it turns into thorium-234, what must be remaining? We'll just do the math, because this works just like a math problem. So the uranium-238 must turn into thorium-234 plus something where the mass number is 4, right? 234 plus 4 is 238. And the number of protons has to be 2. Hey, that's an alpha particle. So that describes the alpha decay of uranium-238. Try this one. What must this be forming? It looks like 2 things are combining, like in a synthesis reaction, but it's all taking place in the nucleus. The math isn't too hard. We should be making uranium-238. Convince yourself that the mass makes sense. This one's getting smaller. We call that nuclear fission. This one's combining. We're calling that nuclear fusion. Analogous to decomposition reactions and synthesis reactions, but completely different since it's all taking place in the nucleus. We also have a handy formula for nuclear decay shown here, where you have the amount remaining, the initial amount, and the number of half-lives. I say a single formula because it does say what n is equal to, so you could squeeze it in right there and make it one formula. This is great for when you have decay going on and you want to know how much you started with, how much you ended up with, or if you have enough data, you could even figure out the half-life. In the case of carbon-14, this has a half-life of 11,460 years. We also have a few problems that you can solve if you're in one of my classes, and this is an introduction to nuclear processes.